Hello, this is Lab 2, Motion of a Falling Object. By analyzing a recording of an object falling to the ground, we can use Tracker to plot its position on the y-axis over time. This visual of observed motion can then be used to create a computational model depicting an object in motion with only the gravity force acting on it, and then with both gravity and the drag force. We can then compare the experimental observations to the computational models to see how our models match what actually occurs. The fundamental physical principles of this lab experiment include Newton's second law, which allows us to calculate the expected future position of the object given the forces acting on it, as well as the gravity or weight force and the drag force. In the case of this experiment, our computational model models the weight force acting on the object alone, and then again with the weight force and the drag force acting on the object simultaneously. Having uploaded my video of the aluminum foil ball dropping to Tracker, I then set the blue Tracker calibration stick length to 1.702 meters, the height of the person dropping it. I then set the coordinate axis at the initial center of the ball with a degree tilt of negative 88.9 degrees to account for the angle of the recording. I then used Tracker to quantify the y-axis position at equal time intervals as the ball fell. From the Tracker data, I determined the ball's initial position of 000 meters and the ball's initial velocity of 000 meters per second. I then altered the code to reflect these values for the initial position and velocity vectors, the value of the g constant, and j hat, indicating the position direction of the y-axis. I began with my gravity model, first altering the overall time to reflect that of the experiment, which was 0.601 seconds. I then coded the weight force, which is equal to the mass of the ball times the g constant times j hat times -1 to reflect the downward direction of the force. Because this is the only force in the model, the net force is equal to the weight force. When the ball's velocity is updated, it will only be affected by the weight force. Here we see the outcome of the coding, the computational model of motion of the object with only the weight force acting on it. For the second model, I added the drag force, which is equal to -b times the velocity squared. The total net force is then edited to include both the weight force and the drag force in this model. I calculated a b value of 0.00218 using a guess and check method to make the final position value of this model equal to that of the experimental observations. Finally, I selected an arrow scale of 70 and added arrows that reflect the magnitude and direction of the forces acting on the object throughout its motion. Here, we see the outcome of the second round of coding, the computational model of motion of the ball, given both gravity and drag force acting on the object. Having already used Tracker to mark and record the y-coordinates of the center of the aluminum foil ball at 19 sequential frames, I created a graph of the observed position values over time. Then, using both the computational models from GlowScript, I took the plotted y-coordinates of the object's motion with only the gravity force, and then again with the gravity and drag force acting on the object. I added the modeled positions onto the same graph, shown here, and compared the results. The graph here shows that the ball does not fall as far as the gravity-only model predicts. However, when corrected with the drag force, the observed and modeled final position are the same, with very little deviation over the entirety of the time. I then plotted the velocity versus time graphs for the gravity model and the gravity plus drag model. Neither of these models predict the terminal velocity. The terminal velocity would be achieved when the weight force and the drag force are equal, and the velocity graph would have a horizontal slope. This could be achieved by increasing the time that the object fell, but given that the short time period of this experiment, the terminal velocity is not able to be predicted as the velocity is constantly changing. In the case that the object has a non-zero initial velocity as it is thrown downwards, the terminal velocity would be the same as when the object is dropped from rest. I created a computational model with a starting velocity of 0, -5, 0 meters per second. As shown in the graph above, given a long enough time, both models converge at the same terminal velocity. This occurs when the force due to gravity and the drag force become equal. The net force then becomes zero, and a constant terminal velocity is achieved. Overall, the results show that the gravity force model overestimates the position of the falling ball. When corrected with the drag force, the final position is the same, but some of the earlier values are underestimated. In the future, a larger but less dense ball could be used to increase the drag force. Despite the slight variations, the computational model is a very close fit, showing that our final model is a good demonstration for our experimental observations.